Hello, everyone. Welcome to the post-contest discussion for Leetcode Weekly. This is Shirgupe. Uh, I hope I am audible. We'll be discussing the problems A to D, that is the four problems from Leetcode Weekly 436. Before that, let's talk about the CP31 sheet. So CP31 sheet is 31 handpicked problems from different rating ranges. We have rating ranges from 800 to 1900. In each rating ranges, you have 31 handpicked problems which are very representative of that rating range, and if you solve them you would get overall good overview of the concepts covered in those rating range. Every week, like, we release 7 to 8 video solutions for these problems. So yeah, like, do check out the CP31 sheet. Let's move on to the first question then. Yeah, all right. The first question was, you are given an n cross n square matrix of integers grid, and we have to return a matrix such that diagonals in the bottom left triangle, including the middle diagonal, were sorted in non-increasing order. That is basically your descending order, and diagonals in the top right corner were sorted in non-decreasing order. So the top bottom left was non-increasing, the top right was non-decreasing, and we had this sample test case. Let's go over it on it. So let's look at the sample test case. So in the first sample test case, like, we were given this grid 173, 982, and 4, 5, and 6. So if you look at the diagonals of this grid, you have 4 diagonals. This is the first diagonal, this is the second diagonal, this is the third diagonal, this is the fourth, and sorry, 5 diagonals. Now the top, like the top right diagonals, so according to our question, we had to sort the bottom left diagonals in non-increasing order. Which are the bottom left diagonals, including the middle diagonal? This is a bottom left diagonal, this is a bottom left diagonal, this is a bottom left diagonal, like left and bottom. So these 3 are the bottom left diagonals, and the remaining are basically top right diagonals. And we had to sort these bottom left diagonals in non-increasing order and these in the non-decreasing order. So let's look at this diagonal. This is like 186. What happens if you sort it in non-decreasing order? Well, non-decreasing, I guess it's, yeah, non-increasing order. Non-increasing, basically descending order. So first take the largest element 8, then 6, then 1. So if you start filling your grid over here, so you take this diagonal, sort it in non-decreasing order, non-increasing order, and fill in the modified diagonal. Then we can take this diagonal 9 and 5. What happens when you sort it in non-increasing order? It remains 9 and 5, basically descending order, 9 and 5. And 4, like the last diagonal is 4. So if you just sort 4 in non-increasing order, it remains 4. There's a single element. Then you can take the top right diagonals. This is 7, 2. So you take 7, 2, and top right, according to our question, we had to sort them in non-decreasing order, basically sort them ascending order. 7, 2 would become 2, 7 then. So you have 2 and 7. Write it in a different color. So you have 2 and 7 over here. And then you take 3, this diagonal. 3 is just itself, no matter how you sort it, it remains 3. So you have 3. So finally, your answer would be 8, 2, 3, 9, 6, 7, and 4, 5, 1 for your, like, output. Like, the output grid would be this. So no doubt set. All right. So yeah, like, that was basically what we had to do in this problem. For this second one too, you could see over here, like, the input grid was this 0, 1, 1, 2, and basically the bottom left diagonals were sorted in non-increasing order and the top right was sorted in non-decreasing order. Now, the constraints over here were like your grid of I could be negative. It can be between minus 10 power 5 to 10 power 5. That is the elements in the grid. And n was up to 10. So there are different ways to solve this problem. But usually in such cases, what we prefer to do is we try to find an invariant over the diagonal. Like what is an invariant? So you take your grid, say it is a 3 cross 3 grid, and say you assign the indices to these grids. So along the x-axis you have 0, 1, 2. Along the y-axis you have 0, 1, 2. Now look at the sum of these things. Okay, if you look at the sum of the first, let's look at the first row. What is this element? This is 0 comma 0, like the position, its index is 0 comma 0. What is sum of 0 plus 0? It's 1. This index has position 0 comma 1. 0 plus 1 is 1. This index has position 0 comma 2. Its position is 0 plus 2, 2. So like this is generally how you would proceed with iterating over a diagonal. Like just assign the indices to elements and then look at the sum of indices on x and y axis. Then 0 plus 1 is 1, 2 over here. And you would have 2, 3 over here. And you would have 3 and 4 over here. And basically, if you keep the indices as it is, you have, if you look at the constant sums, like if you look at all the elements that have sum 0, this is the element. If you look at all the elements that have sum of 1, these are the two elements. If you look at all the elements that have sum of 2, the sum of both indices x and y as 2, these are the elements. Look at all the elements that have sum of 3, you have these elements, these two elements, and all the elements that have sum of 4, you have these elements. So basically you're getting diagonals, but you are getting them in the wrong direction. Basically you are getting diagonals which are in the like top left corner and the bottom right corner, but we want diagonals in this direction, that is from left to right. You are getting diagonals from right to left. If you use the default numbering that we usually use, like 0 to 2 from top to bottom and 0 to 2 from left to right. Now how do you deal with this? Like how, if you can somehow just get this thing to like diagonals going from left to right, then you can just fix a sum and look like what are the elements that have this sum and then get the diagonal elements for that diagonal, and we can figure out like how we'll do that. Use map approach, map of end, vector of end. Yeah, even that would work. So now what you can do is, if you want to reverse this thing, you can just say that, okay, we are taking 0, 1, 2 here and 0, 1, 2 here, like 0 to 2 in this direction, 0 to 2 in this direction. You can reverse direction of any one of these numberings. So for example, what you can do is you can say, okay, this remains 0, 1, 2. And here you're going to reverse the numbering. Like initially you were saying that the first element 0, second is 1, third is 2. Now the first third is 0, next is 1 and 2. Now, if you look at the sum of the x and y indices, then this is 0 plus 2 is 2, 0 plus 1 is 1, this is 0, this is 1 plus 2 is 3, 2, 1, and 2 plus 2 is 4, 2 plus 1 is 3, and 2 plus 0 is 2. Now, if you look at the like constant sum elements, all 2's over here, you will get a diagonal from left to right. All 1's, you get a diagonal from left to right. All 0's, you get a diagonal from left to right. All 3's, you get a diagonal from left to right. All 4's, you get a diagonal from left to right. So if you can basically, now what you can do is you can fix a sum. You can go from 0 to 4. You can fix a sum, say 1, and then you can look which are the pairs of I and j such that I plus j is equal to 1, and then getting all such ij, you will get this diagonal. Also, like there's one thing that we aren't looking at, all diagonals aren't the same in this problem. So you want this top right diagonals and you also want this bottom left diagonals to be different in some way. Now, one thing you can observe is if you look at the diagonals which are at the bottom right, like this, and this, these three diagonals have to be sorted in non-increasing order, and these two have been sorted in non-decreasing order. Now, if you look at the diagonals over here, these diagonals, like the bottom left diagonals, they have sum greater than equal to 2. These things have sum greater than equal to 2. So, and if you just try out a few more matrices, you would basically see that if your numbering is from 0 to n minus 1, so if you have any random matrix of say size n, then your this numbering would be like 0 to n minus 1. This numbering would be from n minus 1 up to 0. And this element would be n minus 1, n minus 1, and so on up to n minus 1. Anything below this thing, it would be greater than equal to n minus 1. Like any sum that is over here, for any diagonal, the sum to the bottom left of this diagonal, sum would be greater than equal to n minus 1. And for any diagonal that is to the top right of this thing, the sum would be less than n minus 1. So what we can basically reason is if the diagonal sum is greater than equal to n minus 1, then you are getting a bottom left diagonal. And in that case, if you're getting a bottom left diagonal, basically you have to sort in non-increasing order. Like in this case, you have to sort non-increasing order. And if your diagonal sum is like less than n minus 1, then you get a top right. And in that case, you have to sort in non-decreasing order. So that was about how you could basically fix these diagonals. So now what you would do is like, what are the possible range of values for a diagonal sum? It can be from 0 to 4 in this case. Now, if you just observe what can be the max diagonal sum, like the maximum index for this x index is n minus 1, for y it's n minus 1. So your maximum diagonal sum can go up to 2 into n minus 1, and minimum is basically 0 plus 0 is 0. What you can do is you can iterate over all diagonal sums from 0 to n minus 1, 2 into n minus 1. Then you say that, okay, this is the sum that we have fixed. Then which I and j satisfy I plus j equal to s. Whichever I and j satisfy that I plus j equal to s, those ij basically would lie on this diagonal. So say you fixed 2, then whichever ij satisfy I plus j equal to 2, those ij would lie on this diagonal. So in that way, you could basically iterate over all of the elements on this diagonal, and basically you can get all the elements, then sort them, and once again iterate over all the elements from top left to bottom right, and see that, okay, assign them in a non-increasing or non-decreasing order. By the way, how would you get all ij? Well, first thing you have to look is when you iterate on a diagonal, assume zero-based indexing. If you assume zero-based indexing, then if you're here at ij, then you're here at I plus 1, j plus 1, and so on and so forth. Now, what can be the values of I? Like, what can be the starting values of I? If you look over here, what can be the starting values of I? Like, I can start at 0, or I can start at 1 or 2 or something like this. So you can basically reason that, okay, you have this sum which is equal to I plus j. When can you assign I equal to 0? Like, when can you start at 0? Well, if you start at 0, then your j has to be equal to, like, if you just insert I equal to 0 into this, your j has to be equal to s. But it may happen that this s is greater than n minus 1. In that case, you can't really have your I equal to 0. So basically what you would do is you can see, okay, uh, like what can be the maximum value of I. So your I is basically, if you just reorder this equation, that would be like s minus j. Your j is at max n minus 1. So you can basically just say that, okay, I is maximum of, either it can be 0, or in case that j even n minus 1 doesn't satisfy this thing, you can just say that I is n minus 1, like s minus n minus 1, and you can get this value of I. Then depending upon that, you can derive an value of j and iterate over all the diagonals by saying that you're over here at I plus ij, then you go to I plus 1, j plus 1, and so on and so forth, until either I or j reach to n minus 1. So Identification is sort in the map approach. Okay. Yeah. All right. So that was the basic idea. The implementation details are like a bit dependent on person to person, like how you implement this thing. So moving on, like how, like one implementation of this approach. So basically here we take the n, that is size of grid, number of rows and number of columns. And you iterate over all the possible diagonal sums. So in the upper triangle, if you look at it, the upper triangle would have sum at most up to n minus 1. So this thing is a different color. So this thing is your upper triangle. So your upper triangle would have a sum of at less than n minus 1. So if you have say 0, 1, 2 and 0, 1, 2, then your upper triangle, that is this part, this would have sum of 1, 1 and 0. Like this is less than n minus 1. So you can just iterate over all diagonal sums less than n minus 1 and they will all lie in upper triangle. And you can iterate over all diagonal sums from n minus 1 to 2 into n minus 1. And they will all lie in the like basically lower right triangle. Also, you can just keep the 2 into n minus 1 because that's a single element. So no matter how you sort it, it just remains as it is. Then for each diagonal sum, this is like the vector of n that, okay, which are the diagonals that we have. Then I and j, assuming zero-based indexing. So what can be I? I can be either like I can either start at 0, or it may happen that if I starts at 0, like your j, the value that j has to take is bigger than n minus 1. In that case, like your I can't start at 0 and has to start below 0. So what would that be? It would be like diagonal sum minus the maximum value of j, that is n minus 1. So this is your value of I. Based on that, you can derive the value of j. So the value of j that I'm using is for like 0 starting here and 0 starting here value. So that's the value of j that I am using. You can even use like the value where 0, 1, 2, like this form of indexing, you can even use this. Then you basically iterate or up till I and j are both less than n minus 1, increment I and j, and fill your diagonals array, sort the diagonals array. For the upper triangle, you have to sort it in non-decreasing order. For the bottom, you have to sort it in non-increasing order. That is like reverse sort. Once you sort it, you once again take out your I and j, once again iterate over all the I and j, and assign the sorted diagonal elements to the grid, like the diagonal. And finally, you can just return your grid. Like that was the first question. All right. Let's move to the second question. The second question was assign elements to groups with constraints. Now, in this question, we are given an array groups where groups of I represented the size of I group, and we are also given an integer array elements. Our task was to assign one element to each group, and basically like we had these elements and we had to assign to each group like one element. And we had these following rules that if you wanted to assign an element j to some group I, that can only happen if that element divides that group, like the size of that group. So if you have a group of size 4, then you can assign it element of like element 2, because 2 divides 4, but you can't assign it element 3. Also, if there were multiple elements that could be assigned, then you have to assign the element with smallest index, like basically the element that comes first in this array. And if there was no element that could be assigned, then you had to assign -1 to that group. And we basically had to follow all these rules and return the assigned array, where assigned of y was the index of the element that was assigned to this group. Also, you could assign an element to multiple groups, so that was allowed. Let's go over an example to like, understand this better. So this is like problem B. So in the first test case, you are given that your groups were 8, 4, 3, 2, and 4, and your elements, they were 4 and 2. Okay. Now take the first element. Take the first element. and try to assign it to 8. Okay, can you assign 4 to 8? Can you assign 4 to 8? Well, 8, 4 divides 8, so 8 divided by 4 is equal to 2, so this is possible. So you can assign 4 to 8. And this element has indices. If you look at the indices, 4 has an index of 0, 2 has index of 1. So 8 would be assigned an index of like 4. Like 4 is the first element which divides it, so it would be assigned index of 0. Then try to assign 4 to itself, like 4 to 4, the second group. 4 divides 4, so 4 divided by 4 equal to 1. So this is like this can be assigned to. So you would assign index 0 to this element. Then can you assign 4 to 3? Well, 4 does not divide 3. Like 4 does not divide 3. So you can't assign 4 to 3, so that's not possible. Can you assign 4 to 2? Again, 4 does not divide 2, so that's not possible again. Can you assign 4 to itself? Yes, you can. Like 4 divides 4. So the last element would have assigned an index of 0. Then next you try to assign 2. 8 has been assigned, 4 has been assigned, and this 4 has been assigned. You only have these two elements. Can you assign 2 to 3? 3 divided by 2 is like 2 does not divide 3. Basically it is something 1 point something, but 2 does not divide 3, so you can't assign 2 to 3. Can you assign 2 to this group, like group of size 2? Yes, you can, because 2 divides 2, so this will be assigned an index of 1. And we are out of elements and 3 hasn't been assigned anything, so you get a -1 over here. And your final element answer would look like 0, 0, -1, 1, and 0. Basically, this says that 8 was assigned an index of 0, 4 was assigned an index of 0, 3 wasn't assigned anything, 2 was assigned index 1, and finally 4 was assigned index 0. That would be your answer in the first test case. Okay, so this is the old one. Yeah, 0, -1, 1, 0. Again, you can repeat the same process for these elements too, and this too. Like basically, what in the most brute force approach, what you do is you iterate over all the elements, fix one element, iterate over all the groups, see if that group is assigned. If it's not assigned, then see if it can be assigned to this element. Like basically, does this element divide the group size? If it does, then you can assign it. Otherwise, continue. Right. Then, okay, so this was first discussed. The next two are similar again. Now, let's look at what we are doing right now and can we implement that outright. Also, the constraints for this problem are that your group's length is up to 10 power 5, your elements length is up to 10 power 5, and both of the group and elements are between 1 to 10 power 5. So basically your uh, number of groups like n, which is like maximum, let's just say it's maximum of number of groups and the number of elements, it's up to 10 power 5. So you can't have a O of n squared solution over here. That won't work. That would lead to a TLE. But you can have an O of n or big O of n log n solution over here. That's okay. And one more thing to note is that the elements of I and the group of I, they are up to 10 power 5. So maybe you can have a solution that is big of element, like the max element, big of max element, or big of max g of I. Even or this into some logarithmic factor, that would work too. So first let's look at what we're doing over here when we derived this solution. When we derived this solution, what we did, you take the first element, iterate over all groups and see, okay, can this element be assigned to some group? So can this element be assigned to 4, to the second group, to the third group, to the fourth group? If it can be assigned, if it's not already assigned, like if it's -1 right now, then you change that to the index of this element and you continue. Now, what that would look like is basically you iterate over all elements, then you iterate over all groups, and say if like basically the group size modulo element is equal to 0, that this element is like this element divides this group, and group is not assigned, then what you do is assign the element to group. Now, what would be the time complexity for this? This would take at most big O of n time, because you have O of n elements, then this would take big O of n time. If you have O of n groups, then this would take big O of n time. And basically, like, you have big O of n outer loop iterations into big O of n inner loop iterations. And this would be a constant time operation. So you are basically getting a big O of n squared time complexity. And that would not work because your n is up to 10 power 5. Okay. If that would not work, then like uh, we somehow have to optimize this thing. Now, one thing is that this is already big of one, so you can't really do much about this. Then we have to find some better way to iterate over all the elements. Now, since we are dealing with like devices, there are like one of the things that can strike your mind is, okay, we have this group, and what we can do is compute all of its devices. So what would that look like? So say your group size is 8. What are the divisors of 8? It is 1, 2, 4, and 8, right? These are the only elements that can divide 8. So your element has to be like whatever element that you assign, it has to be one of these things. All right, it has to be either 1 or 2 or 4 or 8. If your element is 3 or 5, you don't need to consider it because it won't divide it anytime. So like that's one approach. Other approach would be like, then basically what you can do is, okay, you have 1, 2, 4, and 8, then you can iterate over all 1, 2, 4, and 8. See, okay, which of these like first thing you check, does it even exist in the elements array? If it exists in the element array, what is its index? And then you can try to assign that index to 8 and take the minimum of these indices. The other thing that you can do is, okay, uh, like this is one approach where you fix a group, iterate over all its divisors, and try to assign the index of that divisor to the group. The second approach is, okay, you have this element, then you ask which groups would it modify. Like, now the thing is, this approach you would have to use some if you use some maps and some other things, you could get a big of n log n type solution. But since our like max element is bounded above by 10 power 5, you can even use this approach where you basically say, okay, I have groups at most up to like say 100. So like the maximum groups size that I have is from 1 to all the way up to 100. Now I have an element at index say 0, which is 4. Then which groups would it modify? It would modify, like it can be assigned to group number, group with size of 4, group with size of 8, 12, 16, and so on, like all the multiples of 4 up to 100, because after 100 we don't have groups. So we can basically, what you can do is, we can say, okay, we'll maintain 1 to 100 and look at which of these are like, for each of them we'll maintain, okay, what is the assigned index for them, initially assign all of them to -1. Then we can iterate over all the elements that we have, then say, okay, which are the groups which this element will be assigned to, iterate over them. What are these groups? These are basically the multiples of this element. So for 4 it will be 4, 8, 12. For 6 you would have 6 can be assigned to group with size 6, group with size 12, group with size 18, and so on. And then you would have like then you can just once again have this block of logic in there. And finally you would have, like, for each group, what would be the element, the index of element that is assigned to it, and we can iterate over the groups array and calculate our answer. Now for this, the time complexity would be big of n into like log of your max group size, because you're iterating over divisors, and that would be basically like a log of max group size. Also, one more thing that you have to take care of is that if there were duplicate elements like 1 and 1, like all ones, then you may end up iterating over the same array multiple times. So if there were multiple like duplicate elements, but yeah, so they haven't I don't think they have given anything which says that all the elements are unique. So you would have to deal with duplicate elements in the elements array in this case. And yeah, like this was for the second question. Is n of n root n? Well, it won't be n root n because so all right, let's look at it. So for example, let's just say you have your group size, you like your max group size, it's 1 to 100. Okay. Now you iterate over all the elements. The first element, which groups would it modify? It would modify 1, 2, 3, all the way up to 100. That is basically 100 divided by 1. That is 100 groups. If your element has value of 1, then it would modify 100 divided by 1 groups. If your element has a value of 2, then it would modify 100 divided by 2 groups. That is like 2, 4, 6, all the way up to 100. That is 50 groups. If your element has a value of 3, then it would modify 100 divided by 3 and so on and so forth up to 100. If your element is say 101, it won't modify anything because 101 is greater than 100. So at max you have 100 groups. So what would be the total number of groups that you're iterating over? So in case of 100, you have one group. In case of like if your element is 2, you have 100 by 2 groups that you are iterating over. If you have 3 groups, then you are iterating over 100 by 3, like element of size 3, then and so on and so forth. On your 100th element, if you have a element, if you have all of these elements like 1 to 100, it may also happen that you don't have 3, 4, then you won't iterate over them, so you can cancel out those terms. But in the worst case, like you would have an element 1, 2, 3, all the way up to 100. And in that case, you would take these many number of operations. And now the thing is, this sum, the n divided by I from I equal to 1 to n, this is bounded by n log n. So your time complexity in the worst case would be big of n log n, where n is the maximum group size. But yeah, like your worst case time complexity would be big of n log n. Yes, you could say it's a sieve way. One more thing you could do is you can maintain a map from end to end and then say, okay, for like map of D is, this is -1 if D is not in elements, else this is like minimum index of D. And then what you could do is you can iterate over all groups in G and calculate all divisors. Then you can try to assign, okay, like you can try to assign this thing, like assign G with what you could say map of D. Like if G is already -1, then whatever here is, you can just assign it. If G is not -1, you try to minimize the first the index that G is assigned. And you could also do that, but in that case, like it depends upon how you find the divisors of G. If you find it in brute force way, you would end up with a big of n root n solution, basically n for these groups and root n for this. But there are more optimal ways to find divisors too. So in that case, you may like recompute all the divisors and those sort of things. So the one that I have implemented over here is basically you first find the max group size. You maintain your assigned and visited array. And also like one more edge case over here would have been that in at least in the sieve way is that your elements array is all ones. So if there were duplicate elements and your elements were all ones, and if you just like brute force like just plain implement this thing, you may end up doing something like, okay, I have an element of 1, then iterate over all 1, 2, 3 all the way up to group max. Then again we have an element of 1, then again iterate over all, which are all the multiples of 1, that is 1, 2, 3 again up to group max. Then you again get an element 1, again iterate over 1 to group max. To deal with that, you can maintain a visitor array. Okay, which element sizes have you already basically considered, like processed up to this point? So you find the max group size, you maintain the assigned array that you want to like what is the index that is assigned to this group size. Then you maintain the visited array, that which elements have been already processed, like which element values have already been processed. Then you can iterate over all the elements. And if the element is greater than max group size, then there's no point in processing this element, because to assign an element to a group, you have that group size has to be divisible by that element, and it can't be in this case. And if it's already visited, it's already processed, so there's no point in doing this, because you want to assign the minimum index. Then first you visit this element, say that it's processed now. Then iterate over all the group sizes which are multiples of elements. Start with element group size less than equal to max group size, and add element of I to this group size. If this group size is not assigned, then you can assign it with the current index. And since we are like basically iterating from index 0 to n minus 1, we are getting it in increasing order. So we are always assigning the minimum possible index. And finally, you calculate the result vector. So basically in this, what you do is you iterate over all group sizes in group, and just just insert the assigned index for this group size into your result array and return the result array. Let's see. Okay. So that was the second question. Let's move to the third question. The third question was count substrings divisible by last digit. So in this question, we are given a string S consisting of digits, and we have to return the number of strings of S, the substrings of S that were divisible by their last non-zero digit, by their non-zero last digit. And this was the definition of substring, that it's a continuous non-empty sequence of characters within a string. And it was also possible to have that the substring may contain leading zeros. So it was not compulsory for it to be a valid number like with non-leading zeros. Let's look at an example to get a sort of better idea of what we're talking about. And if we look here, now a string was 1, 2, 9, 3, 6, and we had to find all substrings where last digit divides the number, like divides the number that is formed by the substring. For example, if you look at 1296, okay, let's look at all the substrings. First is that 1 by itself is a substring. Now in case of 1, let's look at the number and the last digit. So in case of 1, the last digit is 1. Does 1 divide 1? Yes, it can divide 1. So we are good to go. Then the next substring you can consider is 1, 2. Like this is one substring. So let's look at 1, 2. What is the last digit in 1, 2? It's 2. So your number is 1, 2. Your last digit is 2. Is 12 divided by 2? Yes, 12 is divisible by 2. Like 6 to the is 12. So 12 divided by 2 is 6. So this is a good substring. Then let's look at 29. If you look at 29, what's the last digit of 29? It's 9. And does 9 divide 29? No, like 9 is not able to divide 29. So this is not a good, like not a good substring. So you don't have to count this thing. Then if you look at 93, so if you look at 93, the last digit is 3. Does 3 divide 93? Yes, 93 divided by 3 is 31. So this is a good substring. And so on and so forth. You can basically iterate over all substrings and then find out that, okay, there are 11 such substrings which are good, where the last digit divides the number formed. And that, like we had to find basically the number of good substrings in this thing. And for this, the answer was 11. Also, one more thing was that if your number was say 102 and you are looking at this substring, this won't be a valid substring by default because your last number was not allowed to be 0. So it was given in the question that the last by their non-zero last digit. So this basically implied that the last digit has to be a non-zero number. If it was a 0 number, it was not allowed by default. Okay, so that was basically the question in this thing. Now, if you were solving this in a brute force way, what you could do is iterate from all I from 0 to n minus 1, iterate on all j from say I to n minus 1, then form the number from s from I to j, and check if like the s of j divides number. If it does, then it's a good substring. If it doesn't divide it, then it's a bad substring. Then you could just count these things. Now that would lead to a, like, this is the most basic implementation of this thing, and that would lead to a big of n squared time complexity, because you're iterating over big of n times on I and O of n times for on j, so that would lead to a big of n squared time complexity, and this can be done in big of 1 with some optimizations. But your constraints on the length of s, that is n, were up to 10 power 5. So this won't work. Like O of n squared would not work for this problem. O of n squared won't work for this problem, but O of n or big of n log n can work. O of n root n also probably won't work. Like, it depends on your implementation. Most probably won't work. But sort of the expected time complexity would be in this range, like big of n or big of n log n, or something n into some constant or log n factor. Okay, so now before we even proceed to this thing, like, sort of how do you even approach this thing? Now, in our brute force implementation, you're iterating over all I from 0 to n minus 1, iterating over all j from 0 to n minus 1, and doing some piece of calculation. And these two loops are giving us a big of n squared time complexity. How do we reduce this thing? Like, we can talk about reducing this block later, but first we have to somehow get rid of these two loops, like at least one of them. And if you look at what we are doing over here, we are basically iterating over all pairs. We are iterating over all pairs ij such that I is less than equal to j, and both of them are, like, I and j are in the range 0 to n minus 1. So that's where what we are doing over here. Now, how do you eliminate these two loops and sort of find a way to some better, like big of n or log n way to iterate over the relevant ij pairs? Now, usually what we do in such cases is you try to fix some elements. So say you have fixed j. So what we are doing over here, we are iterating ij and we are fixing I and j. We are fixing both I and j, and then we are doing this block of computation. Now, to remove one of the loops, we can first fix one of these elements. Like, let's just say that we fixed j because we want the last digit. So fixing j would be the good idea. So you have your string s, you have some numbers over here, and you have fixed your j. All right, so you also get some digits, say 2 over here. You have fixed your j. Now you can try to find, like, how many I you have, such that the number formed from s I to j is divisible by the s of j. So how many I you have, such that if you pick that I, if you pick this I, like how many I there are, if you pick this I and take this entire substring, that would be divisible by this s of j, that is 2. We have assumed it to be 2, like this whole thing would be divisible by 2. Now, you can fix j, like you can iterate over j from 0 to n minus 1 and fix j. In brute force way, you would of course iterate from 0 to up to j and fix the I, but we have to find some efficient way to do this thing. All right. How would you basically find efficiently how many I there are such that this is satisfied, and you know you have fixed your j. If you look at what, okay, let's see if there are any doubts. Three, which question? Okay, so we are solving question 3. So we're up to this point. So we have fixed our j. We have the digit that we want to divide by, and we want to see how many I there are. Okay, now let's look at some pair ij, which is a valid pair. So you have this j, and you are at this I. What is the number formed from I to j? Okay, like this is the number formed from I to j. So okay, like we'll pick a string. I guess that would be a that would convey the idea better. So you have this string, and you have fixed your j over here. And now let's consider any I that's say a valid I. Okay, so you have this I over here. All right. What is this number? Like you know that this is j, but what is this number? Like how can you represent this number such that you can iterate, basically get some of get your number of i's in O of 1 or something. So if you look at this number, this is okay, from I to j, the number formed is 1, 2, 2. But you can also represent this thing like this 1, 2, 2 number as 2, 3, 1, 2, 2 minus 2, 3, 0, 0, 0. Okay, why are we representing this as this number? Because if you look at it now, this will remain constant for all I. So even if you are considering I over here, your number form would be like 3, 1, 2, 2. Even in that case, you would have 2, 3, 1, 2, 2 minus this 2, 0, 0, 0, 0. And that would be your number, like the difference of these things would be the number that you are getting. Now, this thing, like this, the first number that you're subtracting from, that is fixed for this j, like this is fixed for j. And the thing that's changing with each I is this number. And now if you look at this number, this 2 or 2, 3, the number that we're subtracting, that's actually the prefix up to I, like up to I minus 1 actually. So that's actually the prefix that we are subtracting up to I minus 1. So your number from I to j is actually prefix up to j minus prefix up to I, and actually some number of zeros. So that's sort of like 10 into j minus I, like some sort of j minus I minus 1. But basically that's how you can represent this thing, where prefix is basically the number that's formed when you start from this and go up to I. That would be your prefix. A prefix of j is fixed, and prefix of I, you can actually pre-calculate this thing. And if you once again like what you can do now is you can pre-calculate this thing, and for each element you don't actually need to consider all the values of prefix. If you look at it, why are we even calculating this number? We are calculating this number so that we can check, okay, is this number divisible by this digit? Okay, so what we want to check is the number, like s from I to j, is it divisible by some digit? Now, since we are talking about a digit over here, what is the range of values of a digit? A digit can be from 0 to 9 at max. From 10 and all, you have a 2-digit number. And also 0 is not considered because our last digit has to be 1. So in that case, we can just skip things. So your digit is actually between 0 to 9. So you have only like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 values for digit. Also, since we are looking at like, is this divisible by 8? What you can do is we can actually store the mod value of this sum, that is this prefix sum. We can store the mod value of this prefix sum, and then for every step that we go forward, okay, so you have this j, you have some prefix of j value, then we can have a frequency array of all prefix of I values where I is like less than j. Then this is your prefix of I for 1, prefix of I for 2, prefix of I for 3, prefix of I for 4, and so on up to j minus 1. And so at this j, like your j value is basically like the sum of the number from I to j. That's basically prefix of j minus prefix of I. And let's just say that we have also updated our prefix of I such that this thing is included in prefix of I. And when is this thing divisible by when is this thing divisible by d? That's the question we are asking. And what we can do is we can store this value modulo d. We can store these values in our array modulo d. And in that case, this sum from I to j, like d divides this sum from I to j, implies that your prefix of j minus prefix of I is equal to 0 modulo d, of course. And that would basically means how many I do you have, like that converts your question to how many I you have, where prefix of I equal to prefix of j. And you can just say that, okay, you can maintain a frequency count of prefix of I, and then for each j, okay, you can look, okay, how many j do we have modulo d, which are equal to prefix of j, like how many I do we have modulo d which are equal to prefix of j. Those many I you would be able to sort of divide, like for those I, like start from I plus 1 all the way up to j. For those I, you could start from I plus 1 up to j, and the number formed, that would be divisible by d. And you'd have to repeat this thing for all the number for all the digits d, and that would sort of give you the answer. Okay. So I hope this was clear. I guess it's a bit confusing for the third one. So just to recap, what we are doing over here is you are trying to say like this prefix of I, you're trying to calculate this prefix of I modulo some digit d, and then you fix a j, you get some digit d over here. Then you say how many I do we have such that your prefix of I modulo d is equal to prefix of j modulo d, and those many number of i's, like add that number to answer your result. Like that is like these many things you would get, like for every such I you would get a substring which is divisible, which has last digit as d, and which is number formed is divisible by d2. And then you can just update your prefix of i's. So up to this point, like up to this point j, you had some certain prefix of I. Then when you go to j plus 1, that is basically adding an extra zero to this prefix of I. So you can multiply your prefix of I modulo d by 10. You can multiply this, the sum that it got by 10, and sort of go on, update your frequency array and go on, so on and so forth. Okay. All right, so for this thing, like how you'd implement it is, first you need a frequency array, like basically what are the number of prefix of I that have some modulo some digit. So you have this TP, basically, okay, you have fixed this digit, like you have the last digit as D, you have some S, then how many I do you have such that the number, the prefix up to that point and some zeros added to the back, that is equal to S modulo this digit D. Initially, you just set all of them to 1. Then you also have to maintain some modulo each digit. you can iterate over all characters, find the digit for that character, update the sum array, update the DP. Now if that digit is greater than 0, then what you do is, okay, modulo this digit, how many I do we have before this j which have sum equal to this thing, those many subarrays you can get, and then you can iterate over all digits and update the frequency array, that is basically your DP array. And like, how would you update your sum array? You can iterate over all modulos and you're adding this digit to your sum. So basically what you would say is, okay, previously this was our sum, now you multiply that by 10 and add a digit at the back, like basically this was your sum right now, 1 2 3. Now if you add a digit 4 to the back, that can be represented as 1 2 3, your previous sum, into 10 plus 4. So that would be how you would update your sum array, and your DP array, which is basically your frequency for that sum modulo that digit, would be sort of, okay, we are calculating the number of prefixes modulo this digit, then iterate over all the sums that are possible for that thing. Now previously you had this sum. Now going ahead, if you go one step ahead, you're basically adding a 0 to this sum. Then what you do is you say 10 into sum, that is adding a 0 at the back, take the mod, and like whichever prefixes had this sum now would have this new sum modulo d. Okay, I think it's a bit confusing. All right, like okay, I guess the explanation became a bit confusing for this number. So basically what look like what we are doing is we are like fixing a j, we get a d, like the last digit that we have. So all right, let me just run over the sample test case and hopefully that would give us a better idea of what we are doing over here. So let's take 1 2 9 3 6. So here we take 1 2 9 3 and 6. Okay, now consider this prefix, like at this point you have no prefix, you only have a 0 over here. So in this case your DP, like the number of prefixes that you have is only 0, and up to j you would get like prefix of j would be 1. So basically like what you can say is, okay, 1 minus 0 equal to 1, and this is divisible by 1, so you're all good. Now shift to next j. What is the prefix for this j? Okay, now when you're looking at this prefix of this j, you are saying what is the prefix up to j? Prefix up to j is 1 2. What are the all the possible i's that we have? One is that the I is -1, that is you don't include anything, like you start from this one, or you can start from this two. In that case, your prefix of I is either you just take nothing, that is just 0, or you remove this one, that is 1 0, or like 2 0 is not possible because we want to have a non-empty substring. So in that case, you can either have like 1 2 minus 0, that is 1 to the complete string, or 1 2 minus 1 0, that is 2 just the last string. Then what you can have is then you can just fix your j equal to 9. In that case, like 1 2 9, what is the prefix of j that you are going to have? Your prefix of j is going to be 1 2 and 9. And what are all the possible prefix of I that you are going to have? Either you start from here, in that case you are only subtracting 0, or you start from this 2, in that case you are subtracting 1 0 0, or you start from 9, in that case you are subtracting 1 2 0. So these are all the prefixes that you have, which you can subtract from this 1 to 9 and get a number. Like 129 minus 0, you get 129. 129 minus 100, you get 29. Or 129 minus 120, you get just the number 9. So basically, by maintaining these prefixes, you sort of get all the possible substrings that you can get from there. And similarly, you can just fix, if you fix j to like 3, then your prefix of j would be 1293, and your prefix of I would be either only 0, like start from 1, or 100, or 1200, or 1290. You can't have 1293 because in that case you're basically getting an empty string. So these would be all the prefixes. Now your number, the value of your number for any fix, by fixing I and j, the value of your number is equal to prefix of j minus the prefix of I, like basically these prefixes. The question is, when is this divisible? When is this divisible by d? Well, this being divisible by d means that this prefix of j minus prefix of I modulo d is equal to 0. So if this is equal to 0 modulo d, then you have like this number, the value of this number is divisible by d. In that case, but that is basically saying that prefix of I modulo d is equal to prefix of j modulo d. All right, if this is the case, then that number is a good number. Also, that number by default, what is this d? Like this d is the last number that you are considering right now. The last digit is 3 over here. So you're basically assigning that to d. So the question is, how do we maintain this thing in an efficient way such that we can get the number of I that satisfy this thing? So if we get the number of I that satisfy this thing, so for example, you have, all right, it would be sort of difficult to calculate over here, but let's just say over here, for now, just assume that 1293 minus 1000 is divisible by 3, and 1290 by 1293 minus 1290 is divisible by 3. But for these two, it's not the case. I'm not getting the exact number, but just assume that this is the case. Then how do you get that there are two such number that satisfy that 1293 minus this prefix of I, like, is equal to this prefix of I modulo 3? Like there are exactly two such number that satisfy this thing. How do you get that efficiently is what we want to optimize up to at this point. Now to do that, what we can say is, rather than storing these prefixes like 0, 1000, 1200, 1290, we can just store their values modulo 3. So this is your prefix of j, that is 1293, and these are all your prefixes of I, like the actual prefixes 0, 1, 1000, 1200, and 1290. What we are saying is, okay, rather than storing this thing, what is my d? My d is 3. Then instead of storing this thing, will just store their values modulo 3. So modulo 10 modulo 3 is like 1. So even this thing is, I guess, modulo 3 is 0, and modulo 3 it's again 1. No, not 1. All right. So yeah, let's just say it's some 2 or something. I'm not like basically to get a better idea. So all these values are modulo 3. This is 0, this is 1, this is 0, this is 2. Now, if this is equal to, say, 2 modulo 3, if the value of this thing, like 1293 modulo 3 is equal to 2, then which prefixes, like for which I would prefix of j minus prefix of I equal to 0? Well, if prefix of j minus prefix of I modulo 3 equal to 0, and your prefix of j is equal to 3, then that implies that prefix of I has to be, sorry, not 3, but say 2. For 3, you can't have a modulo value 3. Is then prefix of I also has to be 2 for this to be equal to 0. So if this mod is equal to 2, then you basically, rather than having to iterate or all of these things, you just have to look, okay, how many prefix of I modulo d do we have such that their value is equal to 2? And you can just directly add that count to your answer, and that would be number of subarrays that satisfy the given condition. Also, if this was like, say, 0, then you would just add the count of 0 over here. And that would be how you do that. Now, one more question that comes is, okay, for 129, so prefix of j for 129, the prefix of I was 0, 1, 0, 0, and 1, 2, 0. Then when you got to the next digit, that is 1293, your prefixes became 0, 1, 000, 1, 2, 00, and 1, 2, 90. Basically, if you look at what's happening over here is all of these guys are being multiplied by 10. So every time you go add a new digit to the back, basically you go do plus plus j, you are getting an extra digit for this sum, and you're also sort of multiplying this, basically adding an extra zero to the back of these prefixes of I, and also adding a new prefix of I. Now, how do you deal with this? What you can do is, so look, one thing that we are maintaining modulo some digit. So we have at most 10 values that we are maintaining. So actually, even though the number of prefixes of I can be large, their modulo values can be only between 0 to 10, some modulo D. So we are basically, what we can do is we can iterate over all of them, multiply that value by 10 and update the frequency such that it will reflect this thing. That's what we are doing over here. Okay, I hope that this explains this better. So yeah, like what we do is we maintain the sum modulo each of the digits, you iterate over all the digits, then update the sum with this digit. So what we do is we iterate over all the possible modulo values, and this then say that basically what will be the new value if you add this digit to the back of the current sum. And also you update the DP, like what would updating the DP look like? Okay, iterate over all the digits and all the possible sums. Then when you go from this prefix to this prefix, what happens is you add an 0 to the back of the sum. So if you add a 0 to the back, that's basically doing a 10 into s, like for every sum. So you can see that in the new DP, whatever contribution this did, that this s did, now it would be 10 into s modulo d once again. That would be its contribution in the new DP. And if d is greater than 0, then we basically add into rest, okay, how many sums, like how many prefix of I do we have such that it's their value modulo d is equal to the current sum, that is prefix of j. And then again, for iterating over all digits, you can once again update the DP array, saying that basically this is like adding this thing like 1290 to the array. So the last part would basically correspond adding 129 over here, and then multiply that by 10, and you would get your new prefix of I. That was clear. Okay. Let's move to the fourth question. So the fourth question was maximize the minimum game score. In this, we are given an array points of size n and also an integer m. And there was another array game score of size n, where the game score of I represented the score achieved at the ith game. Now, initially, each game score was equal to 0. And we started at index -1, which was outside the array at the start. So basically, array was between 0 to n-1. And we could make at most m moves. And in each move, we can either do one of the following things: increment our current index by 1. And after incrementing, we reach at index I, then add points of I to game score of I. Or we can increment our current index by 1, like decrement our current index by 1, and then we can add points of I to game score of I. And we also had to ensure that the index must always remains in the bounds of array after the first move. And what we had to do was maximize the minimum value in game score of I after at most m moves. So let's look at an example to understand this problem better. So we look at this thing. Okay. So here, or like basically initially the game scores would be both 0 0, and our points array was given to be 2 and 4. All right, and the number of moves that we could make was 3. So initially, let's just say that you started at, so now according to the question, you started at I equal to -1. So you basically had these game scores which were 0 0, and your index which is -1 0 and 1. So you started here. In the first move, what you can do is, and also your points were 2, and 4. Now in the first move, what you can do is you can say that you are at -1, increment your current index by 1 and go to 0. And that would also correspond to like add this 2 to this 0. So you were at -1, you did a move, you came to 0, and once you do that, this points would be added to the current game score at this index. So it was 0, it became 0 plus 2 equal to 2. So this thing became 2. Now in the second move, what you can do is, and also you can make at most 3 moves. Now in the second move, what you can do is you are here, you can go ahead. Also, you can't go back. So going back would indicate like going to -1, but you are only allowed to move in this range. So even though you start at -1, you can't go back to -1. You can only move between 0 to n-1. In the second move, you can go from 0 to 1. Now doing that would basically add these points at 1 to the game score, and that would update your 0 game score to 0 plus 4. The value would be 4. In the next case, what you can do is you can once again go back one step. Like in the next move, your current I is here, you can do I -1, and you are at this stage once again. Then this would again like basically add this points of I second time to the game score. So currently your game score is 2. After this addition, it would become 2 plus 2, that is equal to 4. Now you have done 1, 2, and 3 moves, and you could at most make like you could make at most 3 moves. So you are done with your 3 moves. Your array is 4 and 4. The minimum value in this thing is equal to 4, and yeah, like this is your answer. Like the maximum value of this minimum is basically your answer. So 4 is the answer over here, and you do this thing for all different sorts of array. If you look at the second test case too, that's what we are doing. We move from index -1 to 0, add the first point to this array. So you get a 1 over here. Then you move to the second index, you get a 2 over here. Then you once again move back to 1, you get like 1 plus 1, 2. Then you can move ahead. That would give 2 plus 2, 4. And like this is your final array. And what's the minimum value amongst this? It's 2. So if it's 2, then like basically this is the minimum value in this array. And that would be your answer. So what we had to do was we had to find, not find, but we just had to find the maximum value of minimum of this game score after your operations. Now, how would you proceed with this thing? So first thing to notice is that whenever you have to encounter this sort of question, that maximize the minimum or minimize the maximum type, like first thing you have to see, is this thing like monotonically increasing? Like if you can have your minimum value, so the minimum value of G, right? You want to maximize this thing. Let's just say that, and also let's just say that you are given 4 moves. If you can make your G value, what are the possible values of G, like minimum of G? Either G remains 0, or it goes through up to 1, up to 2, up to 3, up to 4, 5, 6, and so on. Like thing you see in such cases, like is this thing monotonic? If you can make your G value at least 2, then you can by default also make your G value at least 1. Like if you can have a set of moves such that your minimum of G is greater than equal to 2, that implies that you can use the same set of moves and have your minimum of G greater than equal to 1 or greater than equal to 0. So if you have defined, let's just say that a check function, like check function of G, basically this returns true if it's possible to have the minimum value of G after some moves greater than equal to x and g, like greater than equal to x. Otherwise, it returns false. And if you look at all the values that this check function returns, then for 0, 1, 2, all the way up to g, you would have some cutoff, like some optimal solution. Up to this point, all of them would return true, true, true. And after this point, all of them would return false, false, false. So basically, our problem has a monotonic structure in a sense that it goes from true, 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 true up to some point, then you have a cutoff, and then all of them are false. So for all of these guys, you can't have any set of moves such that the minimum of g is greater than equal to these things. Then we can basically apply a binary search. We can start with L over here. R is some big value up to 10 power 15, I guess, for this problem. And you can cut off in the mid. You can see if it is true, then you consider this array. Sorry, if it is true, then you consider this array. If it is false, then you consider this array. And once again, try to see the find the cutoff point where the last true is encountered, and that last true would be your answer. Okay. So basically, what we are saying over here is that if we define our check function to be is like check of xg is like the minimum value in g greater than equal to x possible after some moves, then you return true. If we can implement this check function, then we can basically use binary search to find our answer. Now the question is, how do you implement this check function? So now our problem is reduced to given x, make minimum value in g greater than equal to x. All right, so that's our problem now. Now consider the ith element in g. So your g is basically all zeros initially, and your points is basically some things that you have been given. So let's look at the first test case itself. So in first test case, you are given points equal to 2 and 4, and let's just say that you are dealing with x equal to 4. Okay, you're dealing with x equal to 4. Now, if you want to make g at least like the minimum of g greater than equal to 4, then what you have to do is you have to ensure that each element of g is basically greater than equal to 4. And what is each element of g? Like in one operation, what happens is you do g of I plus equal to p of I. Then you can go front, some front, and then once you come back, you once again do g of I plus equal to p of I. So if you basically look, g of I is 0, then it's p of I, then it's p of I into 2, and so on and so forth. Basically, g of I is always a multiple of p of I. And you have to find sort of the first multiple. Like if you operate on the ith element k times, then you get k into p of I. And you want to ensure that every g of I, like minimum of g is greater than equal to x, implies that every g of I is greater than equal to this element x. And if you operated on g of I k times, then you get this value, which is greater than equal to x. This basically implies that your k, like the minimum number of times that you have to visit this g of I, is this upper bound. So for example, we are looking at x equal to 4. We are looking at the g of I is initially all zeros, and we are looking at p is 2 and 4. So if you want to make this element equal to 4, like a minimum of g greater than equal to 4, then at the very least, every element in g has to be 4. Like both of them have to be 4. In that case, how many times does p have to be added over here to make them equal to 4? So over here, if you add 4 exactly once, then that would do. Here you would have to add 2 at least twice. So basically, if you want to make g equal to 4 and 4, you would have to add this 2, 4 divided by 2, that is 2 times, and this 4, 4 divided by 1, that is, 4 divided 4, that is 1 times. So basically, if your p array is 2, 4, if your x is 4, then the number of operations that you have to do on each element would look like 2 and 1. If your x was say 5, then and your p is again 2 and 4, then your number of operations would look like how many times do you have to add 2 into this games array? so that the g of I value is at least 5, you have to add it at least 3 times. So 3 2 is 6. So this would look like 3, and 4 you have to at least 2 times. 4 2 is 8. So this would look like 2. Now you get the number of ops array that, okay, at least these many times this element has to be visited. Okay, at least these many times this element has to be visited. Only then we can have only then we can have this element at least equal to 4. Now look at what happens in this thing. Like, you start at -1, you have 0 1 2 3. You start at -1. In the first move, like, by definition, the first move has to be this thing, that you start at -1 and you go to 0. Here you do like one move, like +1, and one move over here. Then the next move you have to go front, because you can't go back to -1, so you have to go over here. Then you do a +1 over here. After this you have a choice. You can either go to the next element, that is 2, or to the previous elements, that's 0. Then again, if you're at 0, you can just go ahead once again, come back, do something like this. Or if you go to 2, you can once again do 1 2 cycle. So basically what we are seeing over here is, okay, there is some, say, this is like the required number of times you have to visit each element. So you have to visit the first element at least 2 times. You have to visit the second elements at least 1 time. Now, if we can get, like, can we do this thing? Like, can we visit 2 in at most time moves? Can we visit the first element 2 times and second element 1 times in at most time moves? So the first operation is, you come over here, you have visited your element once. Then next operation, you come over here, you have visited your second element once. Then in the third operation, you go back. Now you have visited your first element twice. So you get your 2 1 array, and you took 3 operations. How can we generalize this thing? Let's say you want to visit your first element say 3 times, and your second element 1 times, and you have some other things to be done over here. You come from here, you visited your first element 1 time, second is 0, and all rest are 0 once again. Then you can't go back because this is -1 outside array. You have to compulsorily go front. You visit your second element once now, but you still haven't satisfied this thing. Like, you wanted to visit your first element at least thrice. So you once again have to come back over here. You came back over here, and you visited your second element twice. You still haven't satisfied this thing. You can't go back. So by definition, you have to go front. That's your only choice. So you visited this element twice. Then once again, since this 3 is not satisfied, you have to once again come back and visit this thing. So you have visited this element 3 times. Basically what we are seeing over here is, first time you come back over here, come from back to front over here, and you visit your element once, and you wanted to visit your element 3 times. So this is done. So 3 minus 1, you're still left with 2 times, and for that you can just loop over, go here, come back, you have visited your element once again, go front and come back, you have visited your element once. And once you do that, you are basically at this element. Then once again you can go to the next element, and so on and so forth. So the basic idea in this problem was, okay, first was the binary search part, that if we define that, okay, for this x, can we get a minimum of g greater than equal to x? Then we define this check function, that, okay, can we, like, what is the minimum number of moves that you need to make minimum g greater than equal to x? Then you define this required array, that what is the minimum number of times that you need to visit this element to get minimum value at least this much, and so forth. So yeah, like, and what would the time complexity for this look like? You would get a big O of n into log of, like, the max value, log of 10 to the power 15 for this. So if you look at what we are doing over here is, we say, okay, what can be our maximum min value? That can be either 0, or in the worst case, you perform all the m operations on a single element. Now points of I can be up to 10 power 6. In that case, like m operations and 10 raised power 6, the maximum value of points of I is added to a single game score. That would be your, like, if that's your minimum value, then can be like the maximum upper bound on your answer. You binary search on this thing, like L is less than R, find the mid value. Then we find what is the minimum number of moves with this points array that we need to make such that the minimum value in the games array is at least this thing, med. If it's greater than m, that is the number of moves we have, then we said that, okay, your answer has to be less than this thing. Or if it's less than equal to m, then our answer can be at least this thing. So we increase our L, or we increase or decrease our R. Finally, we just return our L, which is the maximum, like the maximum possible X, such that you can make your game score minimum at least that much. Then how do we check that given this points array, can we get minimum of G, like, to be at least this much? You take your points array, take its size, and then we try to calculate, okay, what is the minimum number of times that you have to visit each index to ensure that its values at least this much. Iterate over all the indices and take the upper bound of this thing divided by points of I. So in each visit, we are adding points of I to the games of I, game score of I, and taking the upper bound, we basically see, okay, how many times, minimum how many times do we have to add points of I to this index so that we get at least this much. And then this is like dealing with a few edge cases. So first you take a total required, basically how many non-zero elements do you have in your required array, and the long rest is basically how many times you have performed your operations. Then iterate from 0 to n minus 1 and also maintain this total required greater than 0. First thing, you increment res. Well, why are you incrementing res? So up to this point, you were at this previous index I minus 1, and now you're coming to I. So you have made one move. Making one move means that you have made one move. So basically one operation plus res. Then if required of I is greater than 0, then your decrement in total required. Total required is basically how many non-zero elements do you have in the required array. Initially that's n, because everything has to be at least 1. And since you have made one move, you have did one operation and your required array, you decrement it. If it's still greater than 0, then you do this cycle. Like if you needed 3 visits to this element at least, by coming from back to front, you have completed one visit. So you have now 2 requirements, like 2 times more you want to add points of I to this element. Then what you can do is go front, come back once. Now you have one requirement over here. Once again, go front, come back. So, and then you are done. Like you have 0 requirement over here now. So this required 1, 2, 3, and 4 moves. Basically, 2 into whatever is the required value up to this point. So if this is greater than 0, then add 2 into, like, do 2 into this many moves this time. That would change our required of I to 0. Also, what this would do is we are also visiting those many times our next element. So if your requirement over here was 2 and the requirement over here was 1, once you go over here, this will become like 2 and 0. Once again, if you come back, this becomes 1 and 0. When you go front, like this would just go on adding points of I to the next element. So this will also decrement your I plus 1's requirement. And if I plus 1 equal to 0, you can decrement the minus total required. Why are we doing this thing? We are doing this thing. So, okay, if you are over here and this was, say, the last element, you went back, you did this thing 2 times, and now you're basically left with 0, 0, and you are at this point. Now you don't want to continue this loop to go front, because if you go front now, you are just basically doing an unrequired move, because all the elements are 0 and you have satisfied your game score requirements. So you can decrement your minus total requirement, saying that one more element has become 0. And if you run out of non-zero elements, then you can stop the loop. Basically, this would be like the minimum number of moves required. So yeah, that was the fourth question, and the time complexity over here would be big of this entire thing would run in big of log of like m into maximum of points. So the this loop would run in that, and this would run in big of n time. So the total time complexity would be big of n into log of m into point max. So these were the four problems. I hope this helped you, and yeah, thank you for attending.